Hello everyone and welcome back once again to this course on aluminum based alloys and metal matrix composites. Okay, so right now we are discussing about the solid solution strengthening, and in the previous class we have seen the different mechanisms by which the strengthening takes place. There are certain interactions which take place, and due to that the hardening or the strengthening occurs due to the presence of the solute atoms. So before we proceed today, let us take a quick recap of the interactions that we talked about in the previous class. So these are the four interactions that we have covered so far. Elastic interaction, which basically arises due to the atomic size difference, which results in a strain field in the lattice, and due to that strain field, the movement of the dislocations is hampered, because as you have seen, the dislocations have a stress field in the core which can be compressive or tensile, and therefore in a compressive field will attract the tensile field around the solute atom and the vice versa, and that is how the motion of the dislocations will be hindered through this elastic interaction. Okay. Modulus interaction is similar to elastic interaction in the sense that the presence of the solute atoms will locally change the modulus, and if the shear modulus of the solute is lower than that of the parent, then it will actually decrease the energy of the dislocation, and that is how the dislocations will be interacting with the matrix, because in that case when the energy is lowered, the dislocations will be attracted to the matrix, and that is how their motion will be hindered. Okay, so that was about modulus interaction. And then we talked about the stacking fault interaction, which comes due to the splitting of dislocations into partials, and when that happens, a stacking fault comes into the gap between the partials, and the solid atoms tend to segregate in this gap, and it will increase the width of this stacking fault. Okay, and higher the width of the stacking fault, it will be more difficult for the dislocations to move, and that is how the segregation of the solute atoms in the stacking fault will hamper the motion of dislocations. Okay, and then we talked about this electrical interaction, which arises due to the valency difference. So in the elastic interaction, it was due to the difference in the atomic size, and the electrical interaction is due to the difference in the valency between the solute atoms and the parent atoms. Okay, so due to a different valency, these solute atoms kind of become charge centers, because the charge will be localized around the solute atoms, and as a result of that they become charge centers, and they will interact with the dislocations which are dipole. Okay, and due to that electrical interaction, the motion of the dislocations will be hindered due to such electrical interactions. Okay, so these are the four kinds of interactions that we talked about in the previous class, but there are two more through which the solid atoms can interact with the dislocations and hamper their motions. Okay, so let us talk about those two. These two interactions basically arise due to the arrangement of the atoms in a particular manner when you have a presence of a different atom, which is the solute atom, right? So let's say we have two types of atoms, A and B. So one of them is the parent and another is the solute. So these two atoms can arrange themselves according to their preference to get attached to similar atoms or dissimilar atoms. Okay, so B can have A as their neighbors and also B as their neighbors. So that will form this AB kind of arrangement. When the dissimilar atoms tend to attach to themselves, that will be AB kind of interaction. And then similar atoms also may tend to have an arrangement in which there will be similar atoms around each of the atoms. Okay, so that will be like BB kind of arrangement where each atom will have a similar atom around them. Okay, so if this is equal, the tendency of having similar or dissimilar atoms, if that is equal, then this will be a random kind of solid solution where the arrangement of the A and B atoms will be random. Okay, so there is no preferential arrangement for the B or for the A atoms, right? They do not really have a preference to have a similar or dissimilar neighbor. Okay. On the other hand, they might also have a tendency to have dissimilar atoms. That is, A will have B as their neighbors, and if that tendency is greater than the tendency of having similar neighbors, then this will be known as a short range ordering. SRO in short. Okay, so if this kind of tendency of having dissimilar atoms prevail over a short range in the lattice, and you have arrangement of A having B as their neighbor, then that is known as the short range ordering. Okay, and a complete opposite scenario of this is called the clustering. That means the tendency of having similar atoms, that means B having B atoms around it, is more than the tendency of having dissimilar atom. Okay, so if that happens, then this is known as clustering. So these two phenomena are opposite to each other. Okay, but either way, they will have a particular arrangement. Okay, either having a dissimilar atom or a similar atom. Okay, so when that happens, the motion of dislocations through a region of short range order or clustering will actually reduce the local order. And as a result of that, the energy of the system will increase. Okay, and in order to sustain this energetically unfavorable dislocation motion, more energy or more work is needed, and that is why you have to apply more stress for the dislocations to move. Okay, and that is how the strength will increase through this kind of short range order interaction. Okay, now this ordering that you have, that might also prevail over long range through the lattice. So in that case, it will be known as long range order. And dislocations can interact with the solute atoms through long range order interaction as well. So if it is only one type of atom, like in pure aluminium, then in the crystal the atomic arrangement are all similar atoms which are arranged in a particular manner according to the crystal structure. But when you have an alloy, you have another atom present, okay? That's the solute atom. So depending on how this solute atom, if you call that as A and this one as B, so depending on how B is arranged with respect to A, you can have either an ordered solid solution or a random solid solution. If the ordering prevails over a short range, we have already seen that is called short range order. And if it happens across long range, that means A will have B as the neighbor across the lattice through a long range, then this can lead to an ordered solid solution, which is also known as a superlattice. Okay, so if we denote A as this and B as the open circle, then this kind of arrangement of the A and B atoms, where they are arranged in a particular sequence, will prevail over a long range in the lattice. Okay, and that is what is known as a long range order or an ordered solid solution. Right, so this will be across all the directions, all the three directions, where you will have similar kind of arrangement. The same sequence will be followed in the other directions also. Right? Now, if there is a dislocation motion through this long range order through the slip plane, then the motion of the dislocation will actually introduce what is called as an antiphase boundary. So let's say this is the slip plane across which the dislocations will move, and as the dislocations move through this ordered lattice, this ordered region of the lattice, it will introduce these antiphase boundaries. Which is also known as APB in short. And now if you see the atomic arrangement, due to the introduction of this antiphase boundary, it will change in this manner. So earlier, if you see here, dissimilar atoms are facing each other, okay, through this ordered region of the lattice. When you have these ordered regions known as superlattice, these also go by the name domain or antiphase domain, and that is why the boundaries between them are called antiphase boundaries. Okay, so across this boundary, if you see now, the arrangement has changed because now due to the motion of the dislocation through this domain or through this ordered region, this antiphase boundary has been introduced, and across this, if you see now, similar atoms will face each other, unlike the superlattice in which dissimilar atoms face each other. Okay, so that's the change which the antiphase boundaries will bring. Okay, and as a result of this, the dislocations will actually split into two ordinary dislocations. And this APB will now have a particular width, which is a result of a balance between the repulsion between these two dislocations. Now one dislocation is split into two ordinary dislocations, and as you know, dislocations of similar sign will repel each other, and the width of the APB is a result of a balance between that repulsion force and the APB energy. And higher will be this energy, more difficult it will be for the dislocations to move, and therefore the stress needed to move a dislocation through an antiphase boundary is given by this particular expression, where tau naught is the stress which is needed to move the dislocation, and it is given by gamma by T, where gamma is the antiphase boundary energy and T is the APB spacing. Right, so that is how, due to the introduction of these antiphase boundaries in an ordered region of the crystal, the motion of the dislocations will be hampered, and as a result of that, the strength of the material will increase. Okay, so these are the 6 different types of interactions which might happen between the solute atoms and the dislocations, which ultimately lead to an increase in the strength, and this phenomena as a whole is known as solid solution strengthening or solid solution hardening. Okay. Now, apart from this strengthening effect, due to interactions with the dislocations, the solid atoms can also give rise to other kind of effects due to some other type of interactions which arise when the mobility of the dislocations with respect to the solid atoms is considered. Okay. So you have seen that the solid atoms are attracted toward the dislocations due to the interaction of their strain fields. Okay. However, the rate at which the solid atoms will move under these attractive forces will be controlled by the diffusion rate. That means how fast or how slow the solid atoms can move through the lattice to catch up with the moving dislocations. So diffusion rate will play a role, and as a result the temperature will also come into picture because diffusion is a thermally activated process. Okay. So now at temperatures at which the diffusion rates are high enough, the solid atoms will quickly move to the dislocations, and if they have mutual attractions, then a second phase may precipitate at the dislocations. And the movement of this nature can be expected to continue until a new equilibrium is reached. On the other hand, if the solid atoms do not combine to form a new phase, then you can expect that a concentration of solid atoms will build around the dislocations. This concentration is higher than the surrounding lattice, and this excess of solid atoms thus associated with a dislocation is known as an atmosphere. So the mobility of dislocations that we talked about, this is basically the movement of dislocations along with its atmosphere. Right? At high enough temperatures, the solid atoms are mobile, and therefore the atmosphere tends to move with the dislocations. And the movement of a dislocation away from its atmosphere will create an effective stress on the solid atoms. So it is a thermally activated process, and the solid atoms, for example, the interstitial solid atoms, if you consider, will have to jump from one position to another position for their mobility. And therefore, solid atoms lag behind the dislocations. So as the dislocation moves, there is an interaction stress which makes it difficult for the dislocations to continue their movement. And therefore, this stress has to be overcome for the dislocations to continue their journey. And this stress is a function of the dislocation velocity. So let us have a look at the effect of dislocation velocity on the drag stress. So this interaction stress is basically the drag stress that arises when the dislocations move and the solid atoms are following them. Okay. So the velocity of dislocations will have an effect on this drag stress, as I said before. So when the velocity is high, there is insufficient time for the atoms to rearrange. And under such conditions, the solid atoms can be considered as fixed obstacles. On the other hand, when the dislocation is at rest, there is no stress between the dislocations and the atmosphere, because the drag which arises due to the competing movement between the dislocations and the solid atoms is absent when the dislocation itself is not moving, right? So now if you provide some velocity to the dislocations, the distance between the atmosphere and the dislocations will increase, and the distance of separation will increase with increasing velocity. Here we also need to consider the effect of temperature, because the movement of the solid atom is thermally activated, and since the drag stress is related to this relative motion between the dislocations and the solid atoms, the temperature will also have an effect on the drag stress. When the temperature is increased, the diffusion rate of the solid atoms will increase, and as a result, the dislocation velocity corresponding to a maximum drag stress also has to be increased. And this can be shown with a diagram like this, with a plot like this. If you plot the dislocation velocity V with the drag stress, it will vary something like this. So this is the maximum drag stress corresponding to a critical velocity of dislocations, which can be called as Vc. When the temperature is increased, the dislocation velocity has to be increased, as I said, for the same maximum drag stress. So if this is in one temperature, let's say T1, if it is increased to T2, then the corresponding plot will be like this. Okay. So this is the critical velocity corresponding to the temperature T2, and this corresponds to the temperature T1. Okay. So to obtain the same maximum drag stress, the velocity of the dislocations has to be increased when the temperature is increased. And you can also see the effect of strain rate, because that is also related to the velocity of dislocations through this relationship. Epsilon dot is the strain rate, and this is given by this expression, where rho is the dislocation density, V bar is the average velocity of the dislocations, and B is the Burger's vector. So you can see that strain rate is directly proportional to the velocity of dislocations, and therefore the plot between the drag stress and the strain rate will have a similar kind of plot that we had for the drag stress versus velocity. So this was an interaction between a solute atmosphere and the dislocations. And such interactions will give rise to some effects which will affect the mechanical behavior of the material, as we are going to see going forward. So that is all I have for this lecture today, but I'm going to see you soon again. Thank you for your attention.